So, second part of the pedagogical introduction, QCD. Before coming to the open problems, I would like to touch the feature of universality, of factorization, sorry, using another point of view, which is the point of view of the so-called operator-product expansion. Maybe some of you have already heard about this, but anyway, again, I will try to introduce you to this problem very intuitively. So, nothing rigorous here, only intuition, and I hope to be as clear as possible. Now, first of all, the justification of this operator-product expansion. Now, you take, for example, our classical example of inclusive deep inelastic scattering. We have an electron scattering on a target. So the electron has an initial for momentum k, goes to the final momentum k prime, exchanges virtual photon carrying for momentum transfer q, and you have an initial target p with momentum p that goes to a final state x, and we sum over x because this process is inclusive. So the scattering amplitude of this diagram is something well known in electrodynamics, so the current of your lepton. So you have initial and final spinors with the gamma mu for the vertex. And then you have the propagator of the photon. We just consider only the simplest case with the photon exchange. Okay, and we have E squared, squared of the charge, and a Q squared for the propagator. And then you have the matrix element of this current operator, J mu, between the initial target and the final state Px. Okay, and then the phase space is built by the final electron at this final unknown state, satisfying the momentum conservation at the 4 momentum level. So P plus Q must be equal to pi x, Px. And then the cross section, what is it? Is the modulus squared of this amplitude times the phase space integrated on all possible final states. So this integral over x is a sloppy notation for meaning the integral of any continuous variable and the sum over any discrete variable that characterize this final state. Okay. Now, since the cross section involves the modulus squared of this amplitude, if you just intuitively look at the graphical representation of this amplitude and you take the modulus squared, you just maybe this thing reminds you that the theorem, the optical theorem, that tells you that the cross section is equal to the imaginary part of the forward scattering amplitude, which is exactly this. If you take this amplitude, you just graphically rotate by 90 degrees and you square, you get this graphic representation of the optical theorem, okay? Because this looks like a Compton scattering, more or less, okay? Now, this blue line here is a notation that means that you have to sum all possible final states. So you have an amplitude here. You see the electron, the photon, and the current. You have the complex conjugate of the amplitude. But here you have the final states. This the electron and this final unknown state. And you have to sum all possible final states. This is the cut diagram notation. Okay, this dashed line is reminiscent of this integral here. And but you can look at this diagram also from another point of view, in the sense that if you look at it is this point of view. So you look at this upper part, you have two vertices, one electromagnetic vectors, this gamma mu, and you have also its complex conjugate on the other side. So from this point of view, you have a tensor with index mu and nu, which is the so-called leptonic tensor that you can calculate in electrodynamics, and then this is the result. And if you look at the bottom part of the diagram, you also have a tensor. You have a current here with index mu, and another current with index nu. And then you can build the hadronic tensor, which is the matrix element that I was talking about, just complex multiplied by this complex conjugate and integrated in all possible final state, consistent with the conservation of the overall moment. Okay, and then you can rewrite this cross section as a contraction between these two tensors. Okay, good. Now, why I say this? Because you can prove, and this is the second homework, if you want, that if you take, for example, this operator, this current operator, J mu, you consider the electromagnetic current of a free quark, sorry. So you assume that this photon interacts with the free quark, a la Parton model-like. Then this current, this is the expression, is psi bar gamma mu psi, typical vector current for electromagnetic interaction. This current is, if you think as an operator, is Hermitian, and you are invited to cross-check that if you take the dagger, you get exactly the same thing. And now, if this, in this condition, you can prove that this tensor can become the Fourier transformation of a matrix element of this commutator between the two currents, but evaluated in two different points. One in the point 0, another in the point psi. 4 points, spatial, not spatial, 4 points. So these are 4 vectors. This psi is a 4 vector. Okay, so this is the exercise if you want to try, and we will discuss it at the end of the day, the solution. Now, why, and this is the crucial point where the justification for the operator product expansion enters, because this, the first observation is that this integral is dominated by short distances. So the main contribution of this integrand is when psi squared goes to 0. Okay. And the problem is that if psi squared goes to 0, this bilocal operator, this commutator is a bilocal operator, is ill-defined in field theory. Now let me show first that this integrand is dominated by short distances. Okay, of course we are working in a deep inelastic regime. So this means that q squared goes to infinity, and the ratio q squared over 2 pi dot q is fixed. But this scalar product can be evaluated everywhere, wherever is most convenient to you. And I'm smart enough, and I choose the target as frame, where this p, this 4 vector, has just the time component, the energy, the mass, and the spatial part is 0, because my target is fixed. And therefore, this ratio is q squared over 2m nu. Okay. And if this must be has to remain fixed while q squared goes to infinity, this means that also nu goes to infinity with the same speed. Okay. Now let's look at the integrand. Now q squared is going to infinity, nu is going to infinity, so this object is increasing q dot psi. No? Q is 4 vector, contains nu, and is related to q squared, so it's going to infinity. But there is a theorem, a mathematical theorem, the Riemann-Lebesgue theorem, that tells me that if this argument of the exponent is increasing, then you have a strong oscillations that cancel the contributions of the various parts of the integrand. Okay, and therefore the final outcome of the theorem is that this the contribution, the main contribution to this integral comes from the areas where q dot psi is limited by a constant, whatever it is, by a constant, so cannot increase too much. Okay. Now, if q dot psi needs to be limited by constants, again, q dot psi is a scalar product, can be evaluated in the most convenient frame. If you, for example, select a center of mass frame where you have no spatial part, so you have cancellation in your bouncing, you have a cancellation of the spatial part, then only the time component of q is different from 0 and multiplies the psi 0. So the time component of the for vector psi for the here. And this must be limited. But we know that nu is going to infinity. So this means that psi 0 must go to 0 at the same speed. Okay. Now, you know that the physics happens within the light cone. So we exclude the space-like distances here because causality prevents for phenomena happening space-like. So we are looking for time-like distances. But if psi square is equal to this because of the metric, and if psi 0 has to go to 0, and this combination must be time-like, positive, it means that also the spatial part squared of the psi needs to be limited and go to 0 with the same speed as psi 0. Okay? So at the end of the day, this condition that gives the dominant contribution of the integral happens only on the very short time-like distances, when psi square is positive and goes to 0, okay? Okay, so this is where the main contribution to this integral happens. But in this limit, this bilocal operator is ill-defined. And the most famous example, the most simplest example is, for example, the scalar theory. If you look at the scalar field theory, and you consider the propagator is a bilocal operator because it depends from two different space-time points, okay? And a propagator is the matrix element on the vacuum of the time-order product of the two fields in two different points, okay? The fields are scalar. And you can calculate this propagator, and you can have the Fourier transformation, and you have the typical 1 over p squared minus m squared structure. The problem is that if x goes to y, so if the condition where the space-like distance between the two space-time points becomes smaller and smaller, then you see that this, if x goes to y, then this is becomes 1, and this integral is divergent. You can directly calculate if you want analytically, and this can be expressed in terms of this modified Bessel function of the second kind plus a delta function. And you see that when x goes to y, this automatically diverges. It's ill-defined. This is where the operator product expansion comes in. Because the operator product expansion basically tells you that the product of two operators in two different space-time points can be expressed as an infinite sum of local operators, which are regular in the limit when the two space-time points collapse together. Okay? And all the divergences are shifted in these so-called Wilson coefficients, because this is dedication to the author of this, first author of this theorem, Wilson, in the mid-60s. And these Wilson coefficients are singular for x going to y. And the sum desummed is ordered starting from the most divergent contribution down to the less divergent one. Okay? And the first contribution is typically the most divergent coefficient multiplied by the simplest local regular operator, which is the identity. This is the usual way to order the terms. And you have already probably seen an example of this operator product expansion when you study the Wick theorem. Have you ever met the Wick theorem in field theory? The Wick theorem tells you that the time order product of two fields, when you take the limit of the two space-time points collapsing, is the normal product of the operators plus the matrix element of the vacuum of the time order product of the fields. And we have seen that this time order product diverges when x goes to y, and it is the first most singular coefficient times the identity matrix element. And the normal order product is an example of local regular operator times a coefficient which is 1. This is an operator product expansion with just two terms. Okay? Now, if we apply this machinery to the inclusive deep inelastic scattering, to our problem, so our tensor expressed as a matrix element of a bilocal operator, that commutator, I don't go into details, it's a long calculation, but at the end of the day, you can, this infinite sum, you can use it to express the hadronic tensor as an infinite sum of powers of m over q. The coefficients, of course, reflect the tensor structure in the Dirac indices, and plus all the set of other quantum numbers that here are symbolized by this alpha between brackets. And the powers, the interesting thing is that these powers are ordered in the m over q expansion is expressed in terms of powers which are related to this object t, which is defined as can be defined rigorously at the twist, which means that it is the canonical dimension of the local operator involved in the expansion minus its spin. So basically, when you expand the infinite sum of local operators, each local operator has a canonical dimension and a spin. Okay? And if you take this difference, you define the twist of this operator. And this is the parameter, the power, which you use to represent this tensor as an expansion in powers of 1 over q. Okay? Good. Now, in other words, what I'm saying is that you have, with the operator product expansion, you have a different way to study corrections to the Parton model. So if you think that the Parton model is a zero order or some theory, if you look at the QCD can be expressed as basically studying all the perturbative expansion of a Parton model in terms of powers of alpha strong. You have leading order, next to leading order correction, next to leading order, et cetera, et cetera. You remember the Wilson coefficients and the inclusive cross-section, okay? But you can also look at the Parton model as the zero order of a new expansion in powers of 1 over Q. So the first term is called the leading twist. It happens when twist is equal to 2. 2 minus 2 is equal to 0, no dependence of Q. This is the dominant part. But then you can have also subleading twists, 3, 4, etc., which count all the powers in 1 over Q that correct your Parton model result. Okay. Now, rigorously speaking, the operator product expansion can be demonstrated actually only for inclusive processes, inclusive DIS, inclusive plus minus, etc., etc. Because if you perform the homework I was giving to you, you will realize at some point that you need to use the completeness of the final states. Integral over x of ket of px and bra of px must become identity. Otherwise, you will never come to this commutator. And this, unfortunately, is not possible for a semi-inclusive processes. But the way out is that you can study the degree of divergence of the fermion propagators in the ion diagram and build a sort of effective diagrammatic demonstration of the operator product expansion that holds also for semi-inclusive processes. And that recovers the results, the rigorous results also when considering the inclusive processes. So that basically people now consider the operator product expansion as a result working for any kind of process, inclusive and semi-inclusive, okay? But the rigorous demonstration works only in inclusive case. Now, why I say this? Because again, as an outcome of a very long calculation, you can prove that the dominant contribution to the hadronic tensor for inclusive DIS comes from this diagram, which is called the handbag diagram. And why I'm showing this? Because again, this is a graphical representation of the factorization. Because the dominant contribution comes from the picture where you isolate the structure of your target, this yellow blob, and you isolate it from the hard interaction between the external probe and a Parton. Okay? So again, there is a factorization between the hard interaction and the structure of your target. Okay? Now, let me say a couple of words on this structure because it will be useful also for the next lectures in the next days about the single spin asymmetry. So this structure is a bilocal operator, which is called the quark-quark correlator. Okay? You see, you have a matrix element where in the target with momentum p, you destroy a Parton because you extract this Parton, and then you project on the final state px. Then you take the complex conjugate, which is this right part of the blob, okay? And then you integrate on all possible final states compatible with momentum conservation. So capital P of the target plus small p of the Parton must be equal to the px of the remnant. Okay? Sorry, excuse me. Small p plus the remnant must recover the initial momentum of the proton. Okay? Because this is an entering momentum, this is exiting, and this is exiting. So small p and px have the same sign. Okay, now using the same tricks that of the homework, you will realize that this is basically you expanded the definition of this delta function, and we realize that this can become a matrix element of a bilocal operator, Fourier transformed. So I destroy Parton in the space-time point x here, and I reinsert it in a space-time point psi. Now, if I take a suitable projections of this correlator, I can extract the various contributions to the structure. The leading twist, the subleading twist at 3, the twist 4, etc. It depends on the kind of projection I use. So this blob contains all of them, all the expansion in powers of 1 over q, and it's just my business to invent the most convenient projection to extract the separate part, the leading, the subleading, etc., etc. Okay? Now, how do I do this? Let me first make a comment, because otherwise the notation will not be clear. So I need to use light-con variables. I hope you know what they are, but in a nutshell, if you have a 4-vector with 4 components, you basically leave the spatial transverse ones, A1 and A2, untouched, and are represented by these A perp. Okay? And then you combine the time-like and the third component into these new components, A plus and A minus. Basically, you are rotating your space on the light cone, where you have 2 light cone bases, and plus and minus, and then you are projecting your 4-vector along these 2 directions, and you get these A plus and A minus components. Why I'm saying this? Because if you look at the inclusive DIS, the fact that you are in a deep inelastic regime, it means that, for example, suppose that your target is initially at rest. This 4-vector is this one. Okay? Then suppose that your virtual photon has the spatial part, the spatial momentum transfer, exactly along the z direction. Okay? And therefore, if you have pz, the z component of p initially is 0, then absorbing a momentum transfer of this kind becomes this. So the final z component has absorbed the modulus of the spatial momentum, q. And the energy has become m squared plus pz prime squared, therefore is m squared plus modulus of q squared. But in the deep inelastic regime, this q is going to infinity. It's much larger than any mass. So I can approximate the square root again with the modulus of q. So this is how your final momentum p prime looks like. Okay? If I compute now the light cone components, I translated this object in light cone components. The p plus is p0 plus p3 square root of 2. So it's square root of 2 times the modulus of q. And the p minus instead is a difference. So if I take the difference of p0 and p3, I get 0. And therefore, the deep inelastic regime, if you read it in the terms of light cone variables, it means that your 4 degrees of freedom problem is reduced to 3 degrees of freedom problem. The spatial transverse one and the dominant light cone component. Okay? You have 1 less degrees of freedom. Now, since P plus is very large because it's connected to the momentum transfer, which is going to infinity, then this justifies the idea of Feynman in the parton model, that if you have a hadron traveling with P plus, all the partons are collinear with it, because this is the most dominant component of your momentum. Okay? And in first approximation, I neglected the transverse components. And that's why this is where my comment gets in our discussion, because if P plus is the dominant component, I take all the partons collinear, P plus, and I can integrate all the other components. And then with this justification, I build this object. You see, it's an integral of the suppressed components of the parton momenta, taking the P plus proportional to the parent hadron P plus component. And then I do the following. I take this quark-quark correlator. This is, if you think in the Dirac space, is a matrix, because I can destroy a parton with index I here and psi I, and reconstruct the parton here with index j, psi bar j, is a matrix. And I take the trace of this matrix with the matrix element of some operator gamma that I have to define. So I build the trace of correlator times this gamma, and I integrate of the suppressed parton components. This object is defined with this notation. Now this is the trick. I can choose capital gamma according to my goals. If I want to extract the leading twist part out of this correlator, I can choose the gamma as this operator, gamma plus. I insert gamma plus here, take the trace, integrate, and what I get is an object which is a leading twist, and it is identified as the unpolarized parton distribution function. So this is the operator definition of the Parton distribution function. But I can go on. I can do the same thing for gluons also, but I can go on to subleading twists. If I choose, for example, this gamma as the identity matrix, I can extract an object at twist 3, which is the PDF E of x. You see it is suppressed with respect to the previous one because P plus is much larger than any mass because it's proportional to Q. So it's suppressed like 1 over Q. And for example, this PDF is connected to the Nucleon scalar form factor. And so I can go on. And I can do also the same thing for polarized, as we will see in a moment. Okay, good. Now, let's come to the problems now, open problems. Now, the first problem is the nucleon mass, okay? Because, why it's a problem? Well, let's come back to the beginning of my lectures. So the standard model, this is the QCD Lagrangian. If you look at this Lagrangian, you know, we have gluons contained in this tensor, F mu, and gluons are massless. Then we have quarks described by this field psi that have this mass m. This mass m comes from the interaction with the Higgs particle, okay? And there is no other mass scale here. Now, what happens? This mass is very small, okay? Here you see the scales. The gluons are massless, and the quark masses, if you sum up the quark in the protons, the up and down quarks, yeah, you get something like a 10 MeV. So in grams is 1.78 to 10 to the 26 grams. So if you compare with the mass of the nucleon, which is 1 GeV, so there is sorry, here there is a wrong, I have to correct this. There is a mistake in order of magnitudes. Anyway, this is should be 170 something in the times 10 to the 26 grams. So you basically realize that the mass of the quarks is roughly 1% of the mass of the nucleons. And since there is no other source of masses, gluons are massless, no other mass scale, then we don't know where this, how to justify this imbalance, because the mass of the nucleon is much larger than the mass of its constituents. Now, actually, there is a solution, there is an answer to this solution, because the rest of the mass comes from the energy of the interaction between quarks and gluons that is needed to confine these objects within the proton. Okay, because we need to spend energy to that, and since relativity is always a good E equal mc squared, this energy translates into mass, and this is where the 99% of the nuclear mass comes from. The problem is that it's very complicated. So it's very nonlinear dynamics that we cannot control within the perturbative QCD starting from this Lagrangian. So this is a cartoon that is produced at CERN. So basically we have a soup of particles that are continuously produced and annihilates around the three main valence quark forming the quantum numbers of the proton. And then calculating this very nonlinear non-perturbative dynamics of the Lagrangians is out of our reach. Only lattice can simulate some observables, but lattice has very strong limitations. Okay? Cannot compute everything. For example, cannot compute observables in the time-like region. Okay, so this is one open problem. So we need to justify where this mass of the nucleon comes from. So the dynamics creates this mass. The second problem is the spin. Okay. Now, to justify the spin, I need to introduce some formalism first. Okay, so suppose we still go back to our inclusive deep inelastic scattering, and we now switch on the polarization, both on the probe, the electron, and also on the target, the nucleon. So the electron is ultra-relativistic. It's so light it travels the speed of light, and basically you can only have the polarization parallel or anti-parallel to its motion. So it's called helicity. And it is indicated here, can be ±1, yes. Now, what about the nucleon? So we define the spin of the nucleon. It's convenient to define the spin of the nucleon orthogonal to its momentum, such that P dot S is equal to 0. And since this object P is time-like, because, for example, when the target is at rest, P squared is equal to M squared, and this is the on-shell, this is the on-shell conditions, in other words. It tells you that P squared is time-like. Then, because of this orthogonality, we constructed the spin as a space-like vector, okay? And therefore, we normalize it, and therefore we have the spatial part is normalized to 1, okay? And this spatial part can divide it between a component which is parallel to the incoming lepton, which is called S parallel, which is built as this vector projected to this cosine of this angle psi, or can be perpendicular to this direction, and therefore you build this using the sine of psi times cosine of this other azimuthal angle phi. Okay, typical parametrization. Now, what happens to the cross sections? So the cross section for inclusive EIS has an unpolarized contribution that we already seen in the previous lecture, but now we have a new contribution that changes form depending on how your polarization of your target is oriented. So if it is oriented parallel, so psi is equal to 0, then we have this parametrization. We indicate the cross section as delta sigma parallel. And then we have a new structure function, G1, entering the business. But this is not the end of the story, because also for polarization, we need two structure functions because it is a spin 1/2 target, exactly as it happens in the unpolarized case. And therefore, and the second structure function shows up if you, for example, polarize your target transverse to the incoming lepton, so psi is equal to pi half, and then you have a cosine of phi component times a combination of this G1 and G2, these two new structure functions, okay? Look, pay attention that now this object is, this component is suppressed because there is this factor gamma tilde here, which is this expression that goes to 0 in a deep inelastic regime. Because Q, nu goes to infinity as Q squared. Therefore, a square root of Q squared, which is Q basically, is, goes to infinity is lower than nu. Therefore, this ratio goes to 0. Okay? So this, in the deep inelastic regime, this component is suppressed with respect to this. Now, again, I have to define a couple of things more in order to introduce the problem of spin. So think of the elementary process where your target absorbs, your nucleon absorbs the virtual photon. Consider this system, okay? The gamma star system. Now we can parameterize the cross-section of this system in terms of the polarization of your virtual photon, this lambda gamma star, and the total angular momentum of your system, suppose it is isolated. And then you can, so the polarization of the gamma star can be transversal longitudinal. This is the origin of these T and L indices here. And the total momentum, intermediate momentum of your system can be 1/2 or 3/2, because you have one, the photon carries unit of angular momentum that hits an object with spin 1/2. And 1 plus 1/2 can, vector sum can be 1/2 or 3/2, okay? And then using this, this parameterization, we can build asymmetries, Helicity asymmetries. If this asymmetry A1 is the difference between the situation where you absorb a transversely polarized virtual photon, but you have intermediate angular momentum 1/2 and 3/2. You take the difference, divided by the sum. The sum is nothing but the unpolarized cross-section. You can prove that this asymmetry is proportional to the ratio between this transfer function and this one, F1. Okay? Then you can also build another asymmetry where in this cross-section you take the interference between the amplitude where you absorb the longitudinally polarized virtual photon and the transverse one, divided also by the unpolarized cross-section. Then you can prove that this object is related to the ratio between the sum of G1 and G2 with respect to F1, but multiplied by, again, this gamma tilde factor. So this asymmetry is suppressed with respect to the other one, okay? Now, the experimentalists do not care about this in the sense that experimentalists measure this inclusive DIS when the spin and prepare the spin of the target either polarized or transverse, okay, with respect to the incoming lepton. Therefore, build these two cross-sections, the sigma parallel and the sigma perp, and can build helicity asymmetries, just taking the ratio between this cross-section and the unpolarized cross-section, which is this one, okay? Now, you can prove that these experimental helicity asymmetries are combination of these two theoretical asymmetries, such that if you measure these two things, okay, you can get, for example, to A1, and therefore to the polarized structure function G1, okay, by starting from experimental data. So you can have experimental determination of this structure function. Now, for last step, you can build the so-called first Mellin moment of this structure function, which means you have data for your G1, and you sum of all possible X that you have reached in your data points. And this is the reason of this integral of the X. And you build this Mellin moment. And you can do the same also from the theoretical side. The meaning on the theoretical side can be easily understood if you look at a very simple situation of the Parton model. In the Parton model, how does this structure function look like? Is that for each flavor, it's the difference of the probability of finding that Parton with fractional momentum of X when its spin is parallel to the spin of the parent hadron, or the difference between the situation where the spin is antiparallel. So for example, in a proton with spin up, I'm looking at the probability when the up quark with fractional momentum X has a spin oriented like the proton or anti-oriented, and I take this difference, okay? So the integral on a possible fractional momentum carried by this polarized quark is indicated as a delta F, and basically it tells you the probability, the percentage of nucleon spin that is carried by that specific flavor, okay? Because I have integrated on all possible fractional momentum. So this is the probability that that flavor on all possible fractional momentums gives you, contributes to the nucleon spin. Then the Mellin moment is the sum of all these contributions weighted by the square of the charge of the considered flavors. Now, in the Parton model, this looks very simple. It's just this, okay? For example, if I stop at the consider just up, down, and strange, it's this. Now, the problem is that I have one observable, experimental observable, so one source of information, but I have three unknowns, delta U, delta D, and delta S. So I have to do something, otherwise my problem is not solvable. And the trick is to involve information from the weak decays of the baryon octet. So the starting point, again, intuitively, is not rigorous. Please forgive me about this. You can rewrite this line in this way. You can check the two things are the same. Okay, I sum and subtract the different things. And now I can identify these three pieces. If I look at the Cabibbo theory that describes the weak decays of the baryon octet, there is a general result, which is a sort of Wigner-Eckler theorem. Basically, it tells you that all the matrix elements describing these decays can be parameterized in terms of only two parameters, the F and D, which are determined by comparing with the branching ratios of these decays. Okay? So these are the numbers with their precision. And then in these terms, you can recognize that this, for example, is the isovector axial current that you can determine looking at the neutron beta decay. And you can parameterize this and indicate it as A3 in terms of these two parameters at F plus D. If you do this is an arbitrary choice, but then all the rest comes as a consequence. Because if you look at this, for example, this looks like an octet current, and it's an octet current related to the hyperon decay, the Xi, the lambda, etc. And then if this is parameterized at F plus D, this octet A8 becomes 3F minus D. And then if you look at the last one, this is the singlet current, the sum of all possible contributions, which is indicated of A naught, but also with the notation delta sigma. And this also becomes 3F minus D. Now, this is very interesting because if you remember the definition of these delta Fs, each delta F is the percentage of nucleon spin carried by that flavor F. So delta sigma is the sum of these things. So this basically summarizes the percentage of nucleon spin carried by all the considered quarks. okay? Now, results. From the theoretical point of view, this thing is the so-called Ellis-Jaffe sum rule, which works in the hypothesis of perfect SU3 symmetry. Now, if you do that and you insert the QCD corrections to these objects, you demonstrate that basically is related to this combination of these two parameters, and you get this number, okay? And for delta sigma, you get this number, 0.6 plus minus 0.12. Now, in 1988, actually the experiment happened in 1987, but the results came out 1 year later. At CERN, there was an EMC collaboration, measured the inclusive deep inelastic scattering of a longitudinally polarized muon on the longitudinally polarized proton, okay? At Q squared 10⁷ GeV squared. They built the G1 of X, and they built the Fresnel moment by summing on the results of the X that could be reached by the experiment. And here you see the plot of the results that you see several points for the Melling moment because they correspond to different values of the minimum X attained by the experiment. So you see that diminishing the X minimum, the value of the integral stabilized towards this value. Okay, they could reach down X down to 0.008. 8 times 10 to the minus 3, something similar. And you see that this value is very different from the Ellis-Jaffe sum rule, which stays up here. Not only, but they calculated delta sigma out of this problem. The error was huge at that time, but you see that the central value is much smaller than the Ellis-Jaffe sum rule. And this is what is called the spin crisis, because this tells you that at this scale, the fraction of nucleon spin carried by the quarks is minimal, is 10%, 12%, okay? So to summarize, in the Parton model, in principle, the quarks carry all the spin of the nucleon. For example, a nucleon with a spin 1/2 in this direction can be reconstructed thinking of the 3 valence quarks where 2 are parallel and 1 is antiparallel, very simple. Delta sigma is 1, so 1/2 of the spin of the nucleon is exactly 1/2 delta sigma, okay? Now, the Ellis-Jaffe sum rule tells you that only 60% of this, because of QCD correction, only 60% of this spin is carried by quarks. And the EMC experiment tells you that at this scale, only 12% of this spin is carried by quarks. So this is no longer true, this equality. So where does the rest come from? So first idea, gluons, okay? And the gluons were polarized gluons, gluon elicities were extracted only recently. And probably Professor Deshpande will mention this. They were extracted at BNL using the relativistic heavy ion collider, considering proton collisions with all polarized protons and measuring jets or pion production in the final state. And since in proton-proton collision, the gluon is available already at leading order, also in a polarized proton collision, you can get to the gluon helicity at 3 level very easily, okay? And so the question is this true? So is the 1/2 spin of the nucleon saturated by the quark contribution, the gluon contribution? Well, to be honest, the answer is we don't know. Why? Because there are errors. And in fact, I mean, if you look at this plot, on the x-axis, you see the integral of the helicity, gluon helicity, when x is between 0.05 and 1. And here, the error is smaller. In fact, you see this band is very narrow. And this is important because this is the first demonstration that at this scale, the helicity contribution of the gluon is, the helicity of the gluon is non-vanishing, is different from 0 and positive. So we have a positive contribution to the spin sum rule. But the problem is that if you look at smaller x, for example, on the y-axis, you see that these results are plotted against the y-axis, where you see the contribution to the same integral when x is between 10 to the minus 3 and 0.05. And you see that here the uncertainty is huge. Okay, the data has very large errors. So we don't know, so we know for sure that the gluon contributes with a positive helicity to the spin sum rule, but we don't know if this is enough to saturate the sum rule. So we are still back to the question, is 1/2 equal 1/2 delta sigma plus delta G? Well, if we trust this number, the answer is no. Something is missing. What is missing? Orbital, for example, the orbital contribution. The fact that the quarks and gluons have an orbital motion also. So this is the first example where the approximation that all partons should move collinear with the nucleon, with the parent nucleon, you remember the parton model and P plus dominance, blah, 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 is broken. Okay? Because if you include the orbital motion, you need to abandon this assumption and include also in your calculation the transverse components of the momenta of the quarks. Okay? But this is not the only example. This introduced me the second open problem, which means I labeled going beyond collinear. The second example is even older than the spin crisis. There are a bunch of very old data on the proton-proton collision in a very simple condition. For example, this is an elastic proton scattering, where one of the two protons is transversely polarized. And I can build an asymmetry when just calculating the cross-section when the proton beam is transversely polarized in one direction or the opposite direction. And I can take an asymmetry, just taking the difference of the two cross-sections. And if everything is symmetric, then this object should be equal to 0. Here you see this A con n asymmetry plotted as a function of the transverse momentum of the final proton. And you see that it's different from 0, very large, 10%, 20%, 30%. This means that according to the polarization of the incoming beam, proton beam, then the final proton can go to the right or to the left depending on this polarization. And this is an evidence of the correlation between the spin of this proton and the transverse momentum of the partons that happened at elementary collision. And therefore is a proof that these partons have an orbital motion. Because with no such motion, no sensitivity to transverse momenta of the partons, this asymmetry would be perfectly symmetric. 0 because the process would be perfectly symmetric, cylindrically symmetric. Okay? So this left and right would be perfectly equivalent. This is not the only example. This is example. This again proton-proton collision with one proton transversely polarized, but producing semi-inclusively a pion in the final state. Now, and again, you can build the same single spin asymmetry. Interestingly, you can calculate this asymmetry in perturbative QCD, and you get something which is very small, because according to perturbative QCD, this asymmetry should scale like the inverse of the transverse momentum of the final proton times the mass of the quarks. And since the mass of the quarks are very small, this asymmetry is very small, order of 10 to the minus 3. And this is not what the experimental data tells you. These are the asymmetries, you see, 40, 50%, and also persisting at very large energies. The square root of S, so the center of mass energy of these collisions, here is 4.9 GeV, 6.6, 19.4, 62.4, here again 20 GeV, but you can have data also at 200 GeV from star that show the same asymmetry, large asymmetry. So another indication that perturbative QCD here is not working, because this framework assumes that the partons are collinear, okay? And therefore any correction is small. Now, chiral load structure. I guess I have to be fast here. So I told you about the projections, the quark-quark correlator, and I told you about the leading twist projection with gamma plus that gives you the unpolarized PDF. But this is not the end of the story at leading twist. You have two more projections if you switch on polarization. You have two more projections. One is with the operator gamma plus gamma 5, and you get the helicity PDF. The third one is the tensor operator, sigma E plus gamma 5. That gives you the so-called transversity operator. And here we come to the third homework. Actually, the third homework needs some introduction that I have no time to illustrate, so I will discuss it at the end of the day myself. And so I will save you this homework. But anyway, the goal is to show that if you insert a project with gamma plus here, you get psi bar gamma plus psi, and this current can be demonstrated that it is basically the sum of the probability densities to finding a right-handed quark and a left-handed quark. So it is an unpolarized. You sum over all possible helicities. But if you take a gamma plus gamma 5, then you end up with the difference of the two densities, which is exactly the helicity, the content of the helicity PDF. And interestingly, if you take the projection with the tensor, you get something which is not diagonal in the helicity, which is very strange, and is named in jargon chiral structure because at this level, chirality and helicity are the same thing. And this is the transversity. Okay, this is the introduction to the homework that I will skip. I will come back at the end of the day in the discussion session. Why we are interested in chiral structure? Because chiral structure since they flip helicity, they are suppressed in QCD, because QCD conserves helicity. And you can realize this looking at the diagram, handback diagram for the inclusive DIS. Here, there is nothing, no mechanism that can allow you to come from helicity plus to helicity minus, or helicity minus to helicity plus. And in fact, the inclusive DIS cross-section contains only two structure functions, which each one corresponds to the unpolarized and the helicity distributions, PDFs. But there is no structure function counterpart of transversity. Why? Because your cross-section is chiral even, and if you want to flip the helicity, introduce a chiral odd object, you need a cross-section of a process where you have another chiral odd partner in order to compensate the transversity. So you need something, a process which is more complicated than this, typically semi-inclusive DIS. You need something in a final state that contains a chiral odd structure. This probably will be source of a discussion in the single spin asymmetries lecture by Andrea Signora. Now, nevertheless, transversity is very interesting. For example, if you look graphically, you see that the two things are similar, just by helicity and transversity, you just make a rotation. But in fact, in a non-relativistic theory, they are equal. So any difference between these two things tells you about the relativistic motion of quarks. Then also in a spin 1/2 hadron like the nucleon, you can't have the transversity of gluons, because the helicity flip of the nucleon, which is a change of 1 unit from -1/2 to +1/2, for example, cannot be compensated by the helicity change in the gluon, because the gluon has helicity 1. So a change would be 2 units, from +1 to -1. Therefore, the transversity of quarks evolves decoupled from gluons. You don't have the coupling of that I showed you for the Diglab equation, and therefore the evolution is very different from the helicity case. This is an overview of the experimental data for the unpolarized structure function F2, the polarized G1, and data available for the transversity. You see that there are orders of magnitude difference of experimental information. We come from thousands of data to hundreds of data to tens of data. Therefore, the extractions of the transversity from data have very large errors. You see, for example, this is the transversity for the valence down quark. Nevertheless, here you see the major groups working on this extraction. They agree that the results for the valence up and down quark transversities are more or less similar. But still, we have very large errors. Why it is important to have smaller errors? Because another object, which is called the tensor charge, which is the Mellin moment of transversity, is important for studies beyond the standard model. Why? Because this object is connected to the matrix element of a tensor operator. It can be computed on lattice and compared with results from phenomenology. There are some tensions in the comparison, but again, this is beyond the scope of these lectures. The important thing is that if you look at the standard model at 3 level, you don't find tensor operators. You never encounter a matrix element like this. Okay? So the idea is that the transversity is still there because we measure, and it is a leading twist object. So the idea is that this could be a footprint at low energy or something happening at a much higher scale, beyond the standard model. An example is, for example, if you look at the weak interactions mediated by the boson, W boson, you can think that this is the high energy theory, that at low energy, when Q square is much smaller than the mass of the W, becomes effectively the Fermi contact term. Okay, and so we are looking here at something that could be memory or something more important. Now, quickly, we have basically two different directions of studies in this way. Studying the Nucleon beta decay, where we introduce an effective Lagrangian with tensor operators. And you can show that this unknown coupling is connected to the isovector tensor charge. So the difference of the tensor charge of the up and down quark. And this tells you which are the scale of this new physics with respect to the mass of the W. And the more precise you know the tensor charge, so the transversity, the better you can determine this product and therefore determine at which scale this new physics should happen. The second direction is the CP violation. There are effective Lagrangian trying to study strong CP violation, to study the balance between matter and antimatter through the electric dipole moment of fermions. And again, you can show that the electric dipole moment of the neutron is a linear combination of the electric dipole moment of quarks weighted by the tensor charges, again. So if you have experimental bounds on the number, if you precisely know these red things, the tensor charge, you can get a precise prediction for the blue things, the quark electric dipole moment, and therefore put constraints of this strong CP violation. Okay. Now, yeah, if you allow me a few minutes, the last topic to introduce the second part of the lecture by Professor Deshpande is nuclear mass effects. So in nuclei, now in system larger than the proton, then the PDFs are not the same as the free proton. So they are different. For example, if you parameterize your nuclear PDF as the sum of the proton and the neutron weighted by the corresponding numbers, Z and N, if you take this ratio, so the distribution divided by the proton one, in principle, you would expect 1 if the nucleons are all independent, one from each other, but you don't. You see that these green lines describe the trend of the experimental data. And this minimum is called the EMC effect. This is the anti-shadowing effect. And here, the small x shadowing. So you have a structure there that tells you that the interaction between color quarks and gluons is different with respect to the proton. Okay? The nuclear matter environment affects this interaction. Okay? And this is one of the pillars of the EIC physics case. To answer to this question, study how this interaction changes in a nuclear medium. Okay? And this is an example of extraction of nuclear PDFs. It works exactly like in the proton case. So you just do inclusive EIS on nuclei. This is the cross-section where now the structure functions have this label A, the mass number. And you fit the data for these structure functions and you extract nuclear PDFs. And these are the most common recent and popular parameterization. You see that in intermediate X ranges, they are similar, but you have a large uncertainties at the borders and also in the channel of strange and gluon. Okay, so we need more data. Where are more data missing? In the low X area. This is the current coverage in XQ squared. And you see that we are missing data here at low X, which is exactly the area where the famous ratio I was showing before is a terra incognita, because we don't know if this curve keeps on falling or saturates somewhere. Data are sitting here in this gray area. Knowing nuclear PDFs is important. For example, will tell you which is the initial condition for heavy ion collisions, for example. And should help in understanding these collective phenomena that are observed in the angular distribution of multiplicity of these heavy ion collisions. This is the famous ridge that happens not only in lead-lead collision, but also in proton-proton collisions. And if you don't know the initial conditions, your nuclear PDFs, then you're stuck. Okay? Then this last topic introduced me the last exotic phenomenon of QCD. What happens to this nuclear matter when you push it to the very high densities and low X, because you have a lot of partons with very low X. Now, the Lagrangian QCD tells us because the gluons are colored, they interact with themselves. So in principle, in these conditions, very high energy, low X, you can have a lot of gluons. They're splitting gluons with smaller X and continuously splitting. And this is the origin of the indefinite growth of the gluon density. You remember the first lecture I was showing you this picture where the red line was the gluon divided by 10. Here on the right, you see the same thing without this factor correction. You see the gluons blows up with respect to all the other distribution, okay? But this cannot happen forever because otherwise it cannot continuously grow because otherwise you violate unitarity. There is a theorem which is called Froissart bound that tells that the total cross-section must grow only as a logarithm squared of energy S of your collision. And if you let the gluon density grow indefinitely, then you violate this. So at some point, these gluons, since they can interact with themselves, they can interact on the reverse. Instead of splitting, they can recombine, okay? Recombine and balance the splitting. So at some point, there should be some terms in the DGLAP evolution of gluon with a negative term that balance the splitting. And this is called saturation. When you reach this equilibrium, this is saturation. The question is at which X and which scale does this happen? We don't know. And this is another pillar open problem of the EIC physics case. And if we discover that, maybe we could discover a new state of gluonic matter in equilibrium between splitting and recombination, saturation. And maybe this could be an universal new state of matter, which would have a very strong consequence, for example, in nuclear physics, because the interior of neutron stars is exactly the same problem. The densities that can be reached there are comparable or even smaller than the densities that you can have here when you go very low X. There is a model in the market, it's called the color gas condensate, that describes this phenomenon and predicts that the saturation scale goes like A over X to the 1/3. Unfortunately, this scale has never been observed clearly and unambiguously so far, neither at HERA nor in other LHC, no other experiments. And this is one of the goals of the EIC. Okay, and this is my last slide. Thank you for the attention.